Overview of transmission line in electronic system. Okay, what has happened now? The revolution of Internet of Things. Okay, some people have their mic on. Please turn it off. If you are not talking, unless you have questions, you can turn it on. Internet of Things. Which is also called IoT. Internet of Things is just like your phone that you have. Phone used to be just phone several years ago, but now you have all kinds of things inside the phone. You have camera, you have pictures, videos, and audio. You can transmit, receive data. So the rate of data has increased. Increasing. So Internet of Things is also something like this. It's like your phone, but it has no screen. Internet of Things has increased the rate of data, right? Because if you want to clock high-speed data, then you need a high-speed clock. You guys have studied a digital system, correct? So have you all studied clock? When clock triggers, the data is read. Things like that. Have you all been through this? So the high-speed clock has resulted in signal integrity issues. Like, for example, if we have a transmission line, and then if you are transmitting some binary data on this side, and then on the other side, let's say if you're transmitting something, some message here, on the other side, you will get some distorted version of the data. What you transmit is not the same thing that is received on the other side. These errors can contribute to the transmission line effect. Transmission line effect, we already talked about what are those transmission line effect. Okay, so this I was talking about transmission line effect. So let's look at a few of this effect. One common failure mode is ISI. So this is called ISI. So what this is, it occurs when pulse spreads out. Okay, whenever you have a transmission line again. On the side, you're sending a pulse. Okay, by the way, guys, this is a pulse. Yeah, this is a pulse. This ideally pulse looks like this. Ideally, this is ideal pulse. But in real life, the pulse will have some rise time. It will take some time to rise. Okay, and then there's also a fall time. Okay, ideally the signal cannot jump like this. It will take some time to rise, and then it will take some time to fall. It's a very small, maybe in nanoseconds. So that's what I mean by pulse here when I draw a pulse that doesn't look ideal. When I spend a pulse on this side, when it comes out on the other side, it looks like this, it's spread out. Yeah, this is the pulse that you're sending. The spread out pulse maybe look like this. And this is called intersymbol interferences, ISI. So again, please realize there's a loss here. There's a loss, signal loss and interference. Signal loss. Pulse spread. So what will happen when this happens? You're going to get checksum error. In digital pulse, when you send, do you know that there's a thing called checksum error? Do you know what is checksum error? It's a detecting error. That means if you send some binary, let's say we send some particular binary number, then the receiver is not able to detect all of them. Like here's an example. Okay, let's say these are some ideal pulse, maybe pulses. Example, binary communication system. Say 1, 0, 1, 1. And then it's going through a transmission line. And then the other side, what happens? You get so this the pulses are spread out. So when they combine, you're going to end up getting something like this. If that happens, that would be a disaster. Are there any questions so far?
No, sir.
No, sir.
Okay, you
No,
see, this
sir.
is the, so this is one of the transmission line effect. A transmission line effect. So we are just looking at some of this effect that you're going to get, is not as easy as you are thinking. Maybe when you get back to work, in those days, maybe you will rarely see RF signals, high-speed signals when you work as an engineer, but you're going to run into high-speed signals quite often because things are moving towards higher frequency. Especially, I told you one of these things were Internet of Things, right? Like Internet of Things, you want to upload something to the cloud, or you want to upload something quickly, and you want to download, you also want to download something quickly and do some other processes. All these needs high data rate, which requires high-speed clock. Now look at another example, another transmission line problem. Ringing. Let's say you have, remember last time in your digital class, you will have a clock input, a digital signal coming. That you have some data, these two lines are data lines. This is maybe a clock trigger, and then you have output. I hope this type of circuit look familiar to you. So in a digital signal, every clock signal, for example, again, I'm drawing a ideal clock signal. So let's say the clock has a period from year to year. Excuse me. Excuse. Clock period. So usually the clock triggers every period. Say, for example, in this case, you are triggering on the rising edge. Clocking on rising edge. So if you are clocking on the rising edge, this is the rising edge. Rising edge is when it goes from 0 to 1, maybe in this case, or some value. So this is the falling edge on this side. This side is a falling edge. Let's say in this scheme, you are clocking on the rising edge. Okay, a nice clock pulse is coming in. And then it is being disturbed due to transmission line effect. You're going to get ringing. I'm not drawing this well. Maybe I'm not drawing this very well. So what happens is the clock triggers on the rising edge, correct? So as soon as the clock rises, it will start clocking here. When it rises, right? The rising edge, it clocks, it will turn on the device to accept some kind of data. And then because of this signal, there's an undershoot here. This is called overshoot. And this is undershoot. Now, because of this undershoot, and there's going to be some kind of ringing. So, and the signals will go up again. The signal will go up again, then it's going to create another rising edge. So that's going to be a double clocking here. You clock twice in one period. This ringing creates another rising edge. So you're going to end up clocking twice in one period. But you guys get the point?
Yes, sir.
Any question on this?
No, sir.
So this is called signal integrity problem, you know. So this is one of the things that people are going to look into very carefully when designing transmission line in the electronic system. I'm just pointing out all these things so that you might be aware of. Okay, signal integrity. We have signal integrity engineers. I don't know if they have this job in Malaysia. Signal integrity engineers will ensure that whatever that you do in simulation, it gets correctly implemented with all these transmission line design taken care of. Signal integrity. A signal can be disturbed by losses, crosstalk, effect, reflection, skin effect, many more. We will look at a few later. We already looked at some before. Here's another example, a realistic example, and you're going to do a lab on this. Okay, this lab is just a simulation lab. Buffer with output impedance represented by Z naught. Okay, a clock driver signal is coming, going through the buffer, and then you have a series resistance followed by the transmission line. So 50 ohms transmission line. And then on the end, you have a load. A capacitive load, a load represented by capacitor. Load represented so voltage across it. Let's say you're taking the measurement at this point. Measured point. You are measuring the output at this point. And then you have a series resistor here. A series termination resistor. A series you have a series termination resistor, and then you have a transmission line is connected to the load. You're going to measure this output. The output is V, voltage across the capacitor. Sorry, just V. You're plotting a V versus time. If Z naught plus RS is equals to 50 ohms. Okay, if this is equals to 50 ohms, the clock signal, let's say, draw the non-ideal clock signal going through. So let's say if this series resistance, if this series resistance plus Z naught is 50 ohms, that means this impedance is matching the transmission line's impedance. There will be no reflection or minimum reflection. In that case, what you expect to be the output? Of course, without if properly matched, then the output is going to be whatever you input. We're talking about assuming there are no other losses. Okay, guys, do you all follow?
Yes, sir.
Any questions so far?
Follow, sir.
If okay, please mute the mic. If Z naught plus RS is less than 50 ohms, then you're going to get ringing, overshoot, undershoot, something like this, okay? Okay, somebody has a mic on, please mute the mic. Who's having the mic on? Not easy to draw this. So you're going to get ringing. Ringing as a signal integrity engineer or data engineer or design engineer, transmission line design engineer. So if you get a signal like this, you should know what the problem is. Okay, if Z naught plus RS is more than 50 ohms, then you're going to get something like this. It's going to go up like this, and then you get a little step here. Then it's going to come down. Then again, there's going to be a little step. And the same, it's going to repeat. Go up here, and then you get a little step, and then. So again, the signal integrity engineer know if the impedance is much larger than the characteristics impedance of the transmission line, he's going to get this signal here, right here. So guys, you all understand this is a very simple circuit. I'm not asking you to design anything. You go to multi-sim. Or you go to multi-sim is maybe the easiest thing to do. Or you can also use ADS if you have ADS. ADS or multi-sim for laboratory lab 1. Lab 1, simulate in ADS. ADS or multi-sim. Do you know any other? Maybe MATLAB also have transmission line. Multi-sim, or what else you know? Simulate the 3 effects. simulate when it's properly matched. Okay, you have to do this because this is very important. Then you can put in your resume that you know how to match a transmission line, how you can match a clock to the transmission line. So this is the clock's amplifier or buffer. And then you somehow, if the amplifier alone may be mismatched to the transmission line, then what do? You put a resistor in series. Then you can play with the value of the resistor to get it matched, to make it 50 ohms. If this sum of Z0 plus RS is less than 50 ohms, you get the ringing. If sum of Z0 plus RS is more than 50 ohms, then you get this type of weird shape here, some steps here. So can you guys simulate these three effects in a transmission using the simulation? Each one of you are going to use a different length of transmission line. All I would like you to do is to show the disturbance in the transmission line, the ringing, and also show this disturbance, and also show how to fix it. So guys, can you see the screen again?
Yes, sir.
Yes, sir.
There's some kind of interruption.
Yes, sir.
Okay, what I was saying was, each one of you, I don't know where you lost me. I would like you guys to simulate this in using ADS or multi-sim or PSpice. Remember PSpice, you can download free. You can easily get a clock, a Z0, get a realistic clock, clock with a high-speed clock. And then with the buffer, amplifier, and RS, your job is to simulate and show that if there's a mismatch between this and the transmission line, then you're going to get disturbance in the transmission, either ringing or some kind of stepped output. Okay, if you then is to show how to fix it by playing with the RS. So this is lab 1. Simulate in ADS or multisim. Cannot have the same combination of RS load capacitor value. Call this CL. Call this CL, load capacitor value, and the transmission line length, TL length. Now what I'm saying is you both try to, each one of you have a different combination. I'm not saying that all of them has to be different. Definitely the load capacitor can be different, right? The load capacitor can be different. Load capacitor can be different, or transmission line length can be different. This can be different. So can have different combination. And then do a video and then send it to me. Just a few minutes video, 3 minutes. Lab report is just video. 3 minutes video. I mean, it can be longer if you want. It can be longer. 3 to how many minutes you want? 3 to 10 minutes video. But try to keep it short. Otherwise, in the WhatsApp, It will take forever. 3 to 5 minutes video. Quickly show. If it's longer, it's fine, but try to keep it short. Just show that you have a disturbance. Show your circuit with the values. Then you show the disturbance when Z0 plus RS is less than 50 ohms. Show the disturbance when Z0 plus RS is more than 50 ohms. And then show how you fix it, how you solve these problems. So once you can do this, then you are qualified to be a signal engineer.